So this is 120 years of Olympic Games data in CSV. So if you load the data, I think it's a big data, so it may take a little while. Okay, so that data is loaded. You realize that is what? It's 271,000 rows, 116. That's a lot of data over 15 variables. Okay. Let's see, maybe let's view it briefly and see how it looks like. EVT, so I've named that as EVT. So you have the individuals, their gender, their age, height, weight, the team which corresponds to the country in which they represent, and whether the game is a summer game or a winter Olympic game, and the year where it was hosted, and the category of sports, and the medal that the individual won. Okay, so that's a lot of data with different categories. So one thing you may want to know is whether there are some missing data points. So if you look at height, it's missing for some people, which is strange. How can we not know your height if you're an Olympic athlete? Anyway, so that's however that happened. It may be that during those times, see 1912, maybe we can understand. Anyway, so if you are going to do descriptive analysis, or you want to avoid missing data values, especially those that are represented by NA or NAN. We have seen the table and we can see that there are some of them there, but maybe if we are not able to see the table, we can check if there's any missing data value. So this line 80 will show us whether, so it's N is.NA will show us whether there's. So line 80 will give us an idea of whether there's any data points that are missing or not. Okay. So if there is, then we can deal with that. So if you run this line, realize that wherever you see true means that there's a data point missing. So you can see that true or false for every column. If you take the ID column there, I don't think there's any data point that's missing, but the data is a very long data set, so it doesn't bring you all of it. It only shows you some parts. But it's an idea. It gives you an idea of what is happening. So if some are true, so all these data points are missing. When you come here, this one is missing. Go up, these are missing. Okay. So for that reason, you want to remove the missing data values for to be able to do a seamless descriptive analysis. Okay. So for that, we want to save the new object as EVT1, and the function is na.omit. So it will go through the data and remove all the lines that are NA. In fact, let's look at the dimension of this data first. Okay, so let's look at the dimension. And we'll see how many. So 271,000. When we finish, we remove the NAs, we'll see how many is left now. So this is supposed to remove the missing values, and we have reduced that to 30,181, which we want to work with. Okay. So that's one data cleaning tip that you may pick. Now I want us to, let me comment this line and see how that works. Show you how that works. Okay. So we know if you look at names here, let me move this up. These are the names of all the objects, the columns in our data frame or in our object EVT1. Okay. Means that we can work with any one of them. But if you want to find the mean of, say, of age, which we clearly see that it's part of the data, we should have an error that we expect. Let's see that error. It says what? Age not found. Okay, age not found, which may be strange, but it's not really strange because we have an object, EVT1, which has attributes, age, name, gender, all of that. So for you to call out an attribute of the data, you need to bind it with the object. And we use the $sign to do that. So if we do the $sign, we will not have the error again. And that's okay. But when you have a lot of lines of code and you have a lot of data variables to deal with, you don't want to be using too many $signs. There's a shortcut that you can use by binding all the columns to the object or to the data frame. And that line is the attached line. Sorry, it's the attached line. So if we attach, now every column in the data frame, we can call it without binding it with the $sign. So now if you do this, it should work. Remember, we can also detach. And also detach EVT1. And if I come back, it shouldn't work because I've detached. Okay. I can reattach and it will work. So that's one thing you want to note as well. So yesterday we saw the different descriptive statistics, the mean, standard deviation, variance. We didn't look at the maximum and minimum, but they are here. We see that there was a 13-year-old who participated in the Olympic Games. Okay, so that's an insight. And the oldest person was 66. That's quite old. Okay, we can later we can pick those ones out. Where is this person from, which country, and all of that. Then we can look at the range. So obviously the range is between the oldest and the youngest. So what we can do is we can just do the max. We did the arithmetic yesterday and mean of age. That should give us the difference. Or we can summarize. So there's a word that summarizes. This summary is not as detailed as we need. So we have the minimum and you have the maximum. In between, you have the median and the mean. And obviously, we have the first quartile and the third quartile. So this is basically showing us how the data looks like if we are to plot it. We can also summarize the whole data frame. And it will provide the mean, median for all the variables in the data. And for most of them, we don't need because some of them are categorical data. So if you look at NOC, for example, NOC is Olympic notation for the countries. Yeah, saying mode is a character. How about names? Names, a character. You are not going to get numerical values for them, but for age and height and weight, you have the rest not useful. That's why you always want to pick out the columns you want to work with. We can also, now that we have cleaned the data, remove the endings, we can save it for future use. So that one goes away. So now let's go into our descriptive statistics. We want to use the past text package. The past text package. Okay. Okay. So what do we want to do? The function is start.disc. So basically start.describe. Okay. Start.describe of what the whole data frame, just as the summary came. In fact, there's one line I missed here. Line 99 is describe that also give a detailed description of the data. So realize that we removed the missing values, so no missing values. They are distinct. The 27 says 7 distinct values. You have the mean, the different quantiles from 5 all the way to 90, the lowest values and the highest values for all the objects in the data. Okay. So when we come here, this basically does the same thing. Okay. So let me speed this one a little bit. Realize that the non-numerical values are NA because the descriptive statistics is basically arithmetic operations. Okay. But we have the number of values, those that are now none because we removed all of them, the minimum, the maximum, the range, the sum, median, standard error of the mean, confidence interval of the mean, variance, standard deviation, coefficient of variation for all the objects. Now, so obviously some of them are uninteresting. If you look at this particular data, the ones that may be interesting are the age, height, and weight for numerical analysis. So you can pick them out and work with as we go along. Anyway, one thing I also want to point out is the notation. See, age, they have all the numbers are presented in standard form or standard notation, and you may not want that, so you can turn it off. If you use this option, this line 112 can turn that thing off. And when we go back and do that, realize that the scientific notations are gone. Okay. But the decimals are also a lot, so you may want to round them off to. So let me use another line. May round them off to some decimal places. So maybe 4 decimal places. Then we put our start.desc, start.disk, and EBT1 now. So that gives us the 4 decimal places. If it's too much, we can reduce it to maybe 2. Maybe 2 decimal places. Why is it not working? Yes, so 2 decimal places or none at all. We can just maybe 0. Let's see. So we have no decimal places at all, which may not be a good representation. So maybe 4 decimal places is fine. Okay. RStudio, it does not easily overwrite the previous objects anyway. So that's fine. And we can pick out individual values to individual columns to work with. So this one is just age, and you realize that with age, we will not have any because all of them are what? Age is a numerical data. Again, so we can round age off to 4 decimal places. For start dot disk of our age, and that's fine. Okay. Now, so this is where we start to look at the distribution of the data. Check the distribution. So to check the distribution, there's an additional argument, norm, equal to true. So we are checking against normality. Okay. Now, what we should note, as I mentioned earlier, is so there's no kurtosis measure for this one, right? But we can get the kurtosis measure. Okay. So there's going to be an additional or a set of additional descriptives that we want to look at. Okay, so if you run this line, there's an error. The error is not our fault. Our data is too big. So it says the test of normality, I'll show you briefly. There's a test of normality in the output, and it's the Shapiro-Wilk test. And that test does not take more than 5,000 data points. So we need to truncate our data to the limit of 5,000 before we can work with. Okay. So that's what is done. In the second line, we need to round. Let me keep this in an object, say T5. And let me round that to about 4 decimal places, T5, 4. List this one. Is it my PC that's slow or what? RStudio is able to print the new specification. You have to run it again. Okay. So this is the what is new, right? So realize that we have a P norm test.p, norm test.ru. So that's the Shapiro-Wilk test we're talking about. We now have skewness and kurtosis, which were not here earlier. And so what is happening is that this skewness and kurtosis value that you have is actually excess kurtosis because we checked against the normal distribution, which is a kurtosis of 3. So that's what you need to check. So just before we go, let me use a new package that will help us calculate the skewness and kurtosis. Then I'll use that to compare that with to confirm the excess kurtosis for you. So there's a package called moments. So I wanted you to stumble upon those packages to use in the task. I have to use this one now. So skewness of age, and we can have a kurtosis of age as well. Kurtosis of age. So realize keratosis is 6.05. Okay, so note that one of age is 6.05. But when we come here, realize that keratosis for age here is minus 1.33. Okay. So this keratosis is actually excess keratosis, not just keratosis. And the difference is too wide. The difference should actually approximate 3. It's possible that they are coming from different packages, maybe the estimations, the formula they use are a little bit different. Okay. But this value you see here is excess keratosis because we are checking it against the normal distribution. Okay. So that is for the descriptive aspect. But let me, before I leave, let me give you an idea of what then the question I'm asking is, one, is this data, if you take age, for example, okay, you saw skewness and you have keratosis. Based on these two, are you going to say the data is a normally distributed data, especially age? And for that reason, are you going to use a parametric approach for inferential statistics or a non-parametric approach? So if you look at the plot, for example, look at this plot. This is the plot for histogram. The histogram for age. Is this one normally distributed or it is not based on the plot? We can see that it is skewed to the right. That's why I have a skewness value of 1.07. There are other QQ plots that will add along the way to describe the data. Yes, the data is not normally distributed, and you want to go ahead with the parametric distribution, then you can transform the data. So if you look at this, for example, it is positively skewed, which means the transformation should be a form of transformation that reduces the data. Okay. And all those transformations, they fall under what you call the box cost transformation. So for example, if you take the log transformation, the log of the data, it's a box cost transformation of lambda equal to 0. So that's if you still want to use the normal distribution. What you can also do is you may center the data, or you convert into standard form. So you have your mean, or you have your standard distribution, standard deviation. So you can take your z, go to x minus mean divided by standard deviation. That will also transform the data for you into the standard normal form that will look more like, in fact, I think we can try that. What was so let's transform to log and then we'll plot and see. So hist of age, but the log of age rather. Do you see how it looks like now? See that this one looks more like a normal distribution.
Yeah. Almost normalized, right?
Yes, almost. So what we can also do is check the skewness of the log of age. That's very close to 0. We can do the same with keratosis. That should also be close to 3. So this is better. So let me just put the note here so we can remember. Transform data. But for the Z, so Z age, our Z or centering is x minus mean divided by standard deviation. So we have our age, which is will be our x, and the mean of age. So let's put mean of age. Let's close all of that. And that's going to be divided by standard deviation of age, right? So that is the new, so we have centered it. So that's also another form of Bosco's transformation, centered. And so the new plot of Z age is going to be, which is strange. It didn't do a lot of help for that. Even the log did better. Okay, so let's have out. Let me check the skewness of ZH back to the original, which means this form of transformation is not the best. It is the log that is the best for it. Yeah, okay, just a little bit. Okay, so that's but let me finish it with the QQ plots, then it will look. So which package? I think maybe this is coming from the normal, the base R. So QQ plot here. We have the QQ now. It's coming from this package called, so let's do the age. So you can actually make this one bigger by clicking on it. That will take the whole page. So you look at it nicer. So if you look at this here, you have the theoretical quantiles on the horizontals and the sample quantiles. That's your empirical quantile. And you want, we are going to put a line in between them shortly. The 45 line. 45 line should be somewhere here. And that will show you that there's a lot of this deviation from the normality. So let's put a line on this one, which is KQ line of age. What color? Let's put red color maybe. Which color do we want? Maybe red. Yeah. So you see there's a huge deviation from the normality. So this data is not normality with it. Let's see how, if we transform it by the log, say blue maybe. Let's QQ line, not QQ plot. Line. It didn't give us the blue. Let me close this plot first. Okay, we need to put this one down, then we'll add this. Okay, we make the plots, then we'll put the line on top. So you see that this one looks better. Even though this is not normally distributed, it is better than before because it's only from this part, the right side, that is deviating from the theoretical normal distribution as compared to the previous one. You can always export this plot as either an image, PNG, or as a PDF, or you can copy and paste it in Word wherever you want it.